Hello, my name is Mrudul and my friend Muktikant today are going to explain you about the model that we have trained, which is detection of vehicle using machine learning algorithms. So in this model, basically we are going to discuss about a machine learning model in which we will see that how AI or the model is going to predict whether there is a vehicle in the given photo or not. Vehicle can consist of any sort of a vehicle. It may be a car, bike, bicycle, or anything. So let's have a look at the test device and the data set that we are going to use for this model. So the data set that we took was from Kaggle.com, which is a big data set consisting of 16,000 photos, which consist and do not consist of vehicles in them. The data set was downloaded locally and was tested on a device which had configurations of RTX 3070 with AMD Ryzen 7 5800H for efficient execution of program. So now let's have a look at the training algorithm. The first lines of code import the necessary libraries including pandas, numpy, OpenCV, random, RE, OS and matplotlib. Now we need to define the variables. The next block of code initializes several variables including label name, images, image path, images pixels, labels and path. These variables are used to store information about the images and labels in a dataset. Loading data. This block of code loads the images from the specified path and store their file paths, pixel values, and labels in the variables defined earlier. It also shuffles the images randomly to ensure the data is not biased. Data exploration. This block of code displays a sample of the loaded images to check if the data has been loaded properly. Data preprocessing. The next block of code splits the data into training and validation set and normalizes the pixel values. Building the model. This block of code defines the CNN model using Keras Sequential API. The model consists of two convolution layers with 32 and 64 filters respectively, each followed by a max pooling layer, a flattening layer, two dense layers with 128 and 64 nodes respectively, and output layer with a single node and sigmoid activation function. Compiling the model. This block of code compiles the model using Adam optimizer. Later we are going to use SGD optimizer and a binary cross entropy loss. Data augmentation. This block of code applies image data augmentation using Keras image detection generator API. Data augmentation helps to improve the model's performance by generating new training samples by applying random transformation to the original images such as rotating, zooming, and flipping. Now we are down to training the model. This block of code trains the model using fit generator method of Keras API. The method takes as input the image data generator object, the training and validation data, the batch size, and the number of epochs. Evaluating the model. This block of code evaluates the model's performance by plotting the training and validation accuracy and losses over epochs. Making predictions. This block of code makes a prediction on new image using the trained model to classify the image as either a vehicle or a non-vehicle. Now I would like to call my friend Muktikant to continue this presentation.
So now we'll take a look at the optimizers, parameter tuning, and algorithms used in this program. We have used ADAM and SGD optimizers, which stand for Adaptive Movement Estimation and Steepest Gradient Descent respectively. The parameter tuning in this code is done through the image data generator function, where various image augmentation techniques are applied, such as rotation, shifting, zooming, and sharing. These parameters are tuned to improve the model's performance by generating more diverse and realistic training data. The algorithm we have used is called CNN, or Convolutional Neural Network, for image classification. CNN. CNN stands for Convolutional Neural Network, which is a type of deep learning neural network that is proven to be highly effective in image classification tasks. In a CNN, the input image is fed into a series of convolutional layers which detect low-level features such as edges and corners, and then more abstract features like shapes and patterns. The key advantage of CNNs for image classification is their ability to learn and detect local patterns in the input image while still retaining a global view of the entire image. This allows them to handle complex images with large variations in appearance and position of objects, making them well suited for a wide range of image classification tasks. ADAM, short for Adaptive Movement Estimation, is an optimization algorithm used in deep learning for stochastic gradient descent. It's an extension of the basic gradient descent optimization algorithm that is designed to provide better convergence rates and faster training times. Now, this algorithm computes individual adaptive learning rates for different parameters, which helps to prevent the algorithm from getting stuck in the local minima. And it is achieved by maintaining an exponentially decaying average of past gradients and their squares, and then using them to update the learning rates on each iteration. This algorithm is particularly effective in large scale deep learning problems as it is computationally efficient and requires minimal memory. It has become a popular choice for many researchers and practitioners in the field of deep learning and is widely used in various applications such as computer vision, natural language processing, and speech recognition. SGD, which stands for Stochastic Gradient Descent, which is a commonly used optimization algorithm in machine learning for training models. It is widely used in various ML tasks such as linear regression, logistic regression, and neural networks. Now, in general, gradient descent is an iterative optimization algorithm used to minimize an objective function by adjusting the model parameters in the direction of the steepest descent of the gradient. In SGD, instead of computing the gradient over the entire dataset, the gradient is computed for a single or a small batch of samples at each iteration. This makes it computationally more efficient than batch gradient descent, particularly when dealing with large datasets. It also has the advantage of being less susceptible to getting stuck in local minima than other algorithms due to its stochastic nature. However, it may require more iterations to converge to a solution. Now, coming to the actual test results, as my friend Mridul said before, we ran the tests of both the algorithms ADAM and SGD on a device equipped with the RTX 3070 and a Ryzen 7 5th gen processor. So as you can see here, each of the algorithms took over 3 minutes to process, so we pre-recorded the results. We can see in the ADAM optimization algorithm, the accuracy values are much higher, which are like approximately twice that in the SGD. And that actually happens because ADAM is essentially just a more efficient algorithm which requires less number of iterations in order to reach a proper solution state or to converge to a efficient solution state. So, as we have seen in the previous slide, after doing all the testing, we can finally compare the SGD and ADAM optimizers which we have used in our project. SGD has an approximate accuracy of 0.49 and ADAM has accuracy of 0.96 approximately, as we have seen before. So the primary differences boil down to these main 3 points, which is ADAM incorporates a momentum term in its update equation, which helps to stabilize the convergence in the presence of noisy gradients. Whereas SGD, though it has the capability to use momentum, it is actually set manually rather than being adapted during training. And that brings us to the next point, that ADAM adapts the learning rate for each parameter individually, whereas SGD uses a fixed learning rate, which may not be optimal for all parameters. Also, ADAM performs optimization using both the first and second moments of the gradient, whereas SGD uses only the first moment. So these round up and conclude all the primary and necessary differences between the two optimizers SGD and ADAM which we have used for this project. So with this here we conclude our demonstration and explanation of the project using deep learning to detect whether we have a vehicle in the given image frame or not using the optimizers SGD and ADAM. Thank you.